Right, so we're going to do a second example. This time a slightly more complicated function, right? It's a little easier to graph a polynomial, I think, just because we have a general idea of how to graph them, right? Where as opposed to a rational function, they can do all kinds of interesting different things, okay? So we'll kind of walk through the steps of graphing. So the first thing that was on the list was to state the domain, and it just so happens that my f has no domain restriction, because when I look at x squared plus 1 and I try to set it equal to 0, my first step is to subtract 1 and I get x squared equals -1, which I'm not allowed to take the square root of. So there's no domain restriction here. So that means my graph of f should be completely continuous, so that'll make it a little less choppy. So the next thing we could find is the intercepts. So if I plug in x equals 0, then I'll have 0, so I'm going to plug in 0 here. When I plug in 0, I get basically 0 over 1, which is 0, and so I get 0, 0. Right? So if I set it equal to 0 over here, I'm still going to get x equals 0, and so this is my only intercept. So maybe I should start my graph here. I didn't do that this time. So my graph will pass through the origin. So there's my intercept. All right. So also, right, if there's no domain restriction, there's not going to be a vertical asymptote, so I don't need to look at that. But I can look at for a horizontal asymptote. So I write the limit as x approaches infinity of x over x squared plus 1, which this will be 0 because the power in the denominator is much stronger than the one in the top. So I end up with 0. So I'm going to get a y equals 0 horizontal asymptote. So when I get out here, basically I should find, it's kind of hard to tell, but my graph should basically approach 0 on both ends. Okay? All right, so ready to get into the calculus now. So I first want to find my intervals of increasing and decreasing. So I'm going to set 0 equal to, I'm going to break apart the numerator and the denominator because I know my critical numbers come where f prime is equal to 0, and f prime would be equal to 0 where the numerator is equal to 0. Here I'm going to end up with x squared equals 1, so x equals plus and minus 1 are critical numbers. And then I can also set this denominator equal to 0, right? But this is the same thing as I had before, which I end up with -1 equals x squared when I do a little algebra there, which there's none, right? So my only critical numbers come from here. So I'm going to put them on my number line here. Here is -1, here is +1. Again, I'm testing in this derivative up here, right? All right, so if I plug in, let's say x equals -3. When I plug in x equals -3, I'm going to get 1 minus 9 on top, which is going to be negative. And then this bottom piece will always be positive, so that means it's going to be negative overall. Right, I have something squared, right? So definitely going to be positive. So when I plug in x is 0, then I'm going to positive over this always positive part. So that means it's positive in here. If I plug in, let's just be symmetric and put in +3, I'm going to get the exact same thing, right? Because it didn't matter because I'm going to square away the negative, right? So if I put in +3, I still get 1 minus 9 on top, which is negative. So I have this situation going on here. Right, so just to write it out formally, I am increasing between -1 and 1. I'm decreasing between -infinity up till -1 and from 1 to +infinity. So that makes, right, that the min, this the max. So I have, let's evaluate these points. I can put them on my graph then. So there's f. So we need f of 1. So f of 1 would be 1/2. F of -1 would be -1/2. Okay, so let's put those on our graphs. So f of 1 is 1/2. So let's say this is 1, and there's 1/2. And f of 1 was a maximum, so I'm going to just put a little bit of a cap on it just so that I know. And then I had -1, -1/2, and so this was a min. All right, so I'm done with my first derivative then. So I'm going to just start this number line down here. So I'll put them all together here, but let's start a new sheet for my second. Well, maybe I can squeeze it on here. So let's put our second derivative on here. So here's my second derivative, right? So I'm going to set each one separately equal to 0. Now, when I've tried to find the undefined places here, this is exactly the same thing that was in the denominator of each one of these, and in each case we found that this can't be 0. So regardless of this power, this still isn't going to give us a 0. So the zeros we're going to get are from this numerator here. So I'm just going to set those equal to 0. So I have 2x times x squared minus 3 is equal to 0. So I'm going to get x equals 0 from this, right? And x squared equals 3 gives me x equals plus and minus the square root of 3. So just for putting it on the graph, the square root of 3 is approximately about 1.7, just for graphing purposes. All right. And for testing purposes, it's always good to know what your numbers are. So there's 0, and let's say that this is the positive square root of 3, and then this is the negative square root of 3. And we'll put in parentheses here 1.7, and then this is negative 1.7. Okay, so I want to pick a number back here. So let's say I'm just going to plug in x is negative 3. All right, so we're up here, right? This one down here, right, when I square something and add 1, I'm always going to have a positive number. And when I cube it, I'm always going to have a positive number. So what's going to happen is up here. Okay, so if I plug in x is negative 3, then this will be negative. I'm going to have positive underneath. And then I plug in here, and it will be positive. So I end up with a negative interval overall. Let me put it up here. All right, now between here, let's say I'm going to choose negative 1, because that's the only nice integer in between them. If I plug in negative 1, this will be negative. This will also be negative, and then this is positive. So that makes negative times negative on top is positive. Over positive gives me positive in that interval. Right, if you need to evaluate it, just go ahead and do that. If I have x equals positive 1, then this is positive. This will be negative, because this will be negative 2, and then this is positive, making it negative. Right, so my concavity is changing. So concave down, concave up, concave down, and then let's see. So does it follow the pattern? If I choose x equals 5, for instance, that's positive, positive, and it does. So that means, just to write my intervals of concavity, I'm concave up in here between negative radical 3 and 0, and here, which starts at radical 3 and goes to infinity. Down in the other parts, which is from negative infinity up until negative square root of 3, and between 0 and square root of 3. All right. Okay, so that means we have, let's see, points of inflection here, here, and here. All right, so this is a point of inflection, right? I already knew that. And so I'm going to need to evaluate my function at square root of 3 and negative square root of 3. Oh, good. Okay, so f of square root of 3 gives me square root of 3 over, let's see, I'm going to square square root of 3, and that's going to give me 3 plus 1 is 4. All right, and then f of negative square root of 3 gives me basically negative square root of 3 over 4. All right, so I decimal approximated square root of 3 over 4, just for rough sketch. This is approximately 0.4, and this one is approximately negative 0.4. So we'll put those on our graph now. Okay, so let's see, that was at square root of 3, and square root of 3 was approximately 1.7. So there is 1.7 and 0.4. So that means it's just down, because this was 0.5, right? So this one's just about, well, that's a little bit farther over for 2. We'll say it's about right here. Okay, so this is a point of inflection, and then we also have one that is 1.7, so about here, and then a little bit, not quite as low as that one, about here. Okay? Okay, so now we're ready to put all of these things together. All right, so we get negative 1 and 1 from my first derivative. I'm putting that on my just everything on the number line. I'm going to have the 0 in between. And then I've got negative square root of 3 out here and positive square root of 3 out here. So there's all my critical numbers of both the first and second derivative. So let's put first the first derivative on. Right, so I'm going to write first derivative, second derivative, and I'm just looking at the signs here. So up until this negative 1, my first derivative is negative. So it's negative in this interval and it's negative in this interval. And then it turns positive here, right? And it goes positive until I get to positive 1. So that means it's positive in this interval and positive in this interval. Then it's negative after that. So that means it's negative in this interval and this interval. So that's my first derivative. So now I'm going to look at my second derivative here. A little bit more complicated, right? But it's concave down, so negative out here to the left of negative square root of 3. So that means I'm negative negative here. At square root of 3, between square root of 3 and 0, it's positive. So that means in this one here and this one here. And then on the right of 0, up until square root of 3, it's negative. So I have negative in this interval, negative in this interval. And then square root of 3 here is positive, so that means it's positive in this last interval. All right, so here we go. Now, one thing to remember is that I am going to have a horizontal asymptote at y equals 0. Right, so that means that my end behavior should be approaching right here. All right, so from out here, knowing that this is down here, my limit as x goes to negative infinity is the same. It also approaches 0. So let's see, I am decreasing and concave down. Okay, so decreasing and concave down is this picture right here, right? Until I get to square root of 3, so right here. So that means my vertical or my horizontal asymptote says I should be here, and then I'm decreasing and concave down until I get there. I should have made my graph a little bigger. Sorry about that. All right, so now in between these 2 points, I am decreasing and concave up. So that means I have more of this tilt, which is good because I need it to be the min, right? Then from negative 1 to 0, I am positive positive, meaning I'm increasing and concave up. So that means I do this. From 0 to 1, still increasing, but concave down. So it has a piece that looks like that. From 1 to positive radical 3, it's decreasing and concave down. So it looks like this. And then I am decreasing and concave up. And again, I'm approaching a horizontal asymptote, so decreasing and concave up looks like this. A very interesting looking graph, right? So that's how we put it all together.